Today we will learn what is the difference between a position time graph and a displacement time graph. How can we create a displacement time graph from a velocity time graph, and how can we determine acceleration from a velocity time graph? Let's get started. Let's start out by talking about how to make each of these things. We have our mixture of velocity and time, and we want to make two things, displacement and acceleration. Well, in order to make displacement, we can use velocity and time, and to make acceleration, we can also use velocity and time. The way that we create them is just different. In order to make displacement, we're going to multiply velocity and time because we can see by definition of velocity, if we multiply time to the left-hand side, we'll get displacement. And in order to get acceleration, we just need to divide the velocity in time. Because by definition of an acceleration, we know that the change in velocity divided by the change in time gives us that value. Now, how do we see this on a graph? In order to get displacement, we can find the area under the curve because this will have us multiplying our x and y values, which in this case are velocity and time. In comparison, in order to get acceleration, we're going to calculate the slope of the velocity time graph because the slope is rise over run, which is delta v over delta t, which is perfect. Now, really quickly, I want to highlight why we're going to be talking about displacement time graphs today instead of position time graphs. The first thing to know here is that displacement time graphs describe how far away an object ends from where it started, right? That's the definition of displacement, and it's in some given amount of time. In comparison, what we have been looking at is position time graphs, and they identify the known locations of an object after each second. I have a really great video that breaks down everything you need to know about motion time graphs, and I'll link it above. It's awesome. I highly recommend watching that video if you haven't seen it yet before you watch this one. The thing about displacement time graphs is they're usually created from velocity time graphs. It's the one time that we tend to use it because as physicists, we want to give ourselves the most data that we could possibly access. And the truth is that displacement time graphs have a limit to the amount of information that they provide us. In comparison, position time graphs give us so much knowledge. We know the initial position of the object, and we can determine its location at any point along the graph that is provided. In comparison, displacement time graphs are kind of limited because the reality is it'll tell you how far away the object moved from where it started, but the key thing that it doesn't tell you is where you actually started. In comparison, position time graphs provide all that information and they can be used to create all of their motion time graphs. So they just provide us with a little bit more. Now let's talk about how to calculate displacement from the velocity time graphs. There's three main shapes that you will see. There's constant motion, where our initial and final velocity are equal. This will create a flat horizontal line. And you can see here, because V naught equals V final, I've just labeled it V naught, and we have over some given time T naught to T final. Now that will produce a square or rectangle, and the area of a square rectangle is going to be base times height. Our base is our time, so delta t, and our height is our velocity, in this case v naught. And so we would plug that in and we will get our displacement. Now, the next one is accelerating motion, where your initial velocity is 0, so you start at rest. This is very common in physics, and it's a situation that you usually start out with when you're looking at acceleration. In this case here, you'll see it starts at the V naught is at 0, and then it increases over time to V final at T final. In this case, we're looking at a triangle though, and that's 1/2 base times height because it's half of a rectangle. In this case here, we have displacement is equal to 1/2 delta V times delta T, because in this case, our height is going to be V final minus V initial, and T final minus T initial is our base. Now, the last scenario is the most complex, which is the case where your V naught is not 0, right? This means that your initial velocity is greater than 0. And in this case, what's going to happen is you're going to see that you start above the x-axis or below. And what that means is that you're going to end up having two different shapes. You're going to have a triangle at the top, and you're going to have a rectangular square closer to the x-axis. And so in this case here, you would just do the constant motion shape, and you would have also the triangle shape. And you can notice that if we were to add those two areas together, we'll get our total displacement. So in this case, it's base times height plus 1/2 base times height of the triangle above. These heights are different. That's the key thing that I tried to highlight in this picture here. Our original height is v naught, where because it's going to be v naught minus 0, but that's always just your initial velocity times the amount of time that has passed. And then you're also going to calculate the area of that triangle by doing delta v, v final minus v initial, times delta t. Okay, with that set in motion, let's go ahead and look at some examples. Now let's start out with the most simplistic and we'll work our way up to the most complex. The simplest setup that we can have is this one. It's where our velocity is 0. That means there is no motion. We can see v naught is 0, v final is 0, and we're looking at a time interval of 5 seconds again. In this case, we can calculate acceleration using our definition, but 0 minus 0 divided by 5 minus 0 is just 0. So in this case here, no motion is going to produce an acceleration of 0 as expected. Now here's the thing though. When we go to calculate our displacement, if our acceleration is 0, we're looking at constant motion. So I'm going to choose to calculate the displacement of a rectangle. But in this case, our initial velocity is 0, so our displacement is 0 because there's no area under the curve due to the fact that our line is on the x-axis. So as you can see here, in our no motion scenario, this creates a bunch of graphs at 0. Let's look at a different example of constant motion that has a little bit more to offer. Now, let's say in this case that we have an initial velocity of positive 3 meters per second. We can see it's constant because our velocity stays the same. And in this case, uh, we're looking at another 5-second interval. Now, if I were to calculate acceleration, because it's constant motion, I'm still going to get an acceleration of 0. So that part stays the same. However, we can see now that there is going to be an area under the curve between our 3 and 0 point on the velocity time graph. So in this case here, we could calculate this is a rectangle and it's constant motion. So I would do my v naught is 3, my T final is 5 minus 0, which is just 5, and 3 times 5 is 15 meters. So my overall displacement is going to be 15 meters. Now you can use this formula and you can calculate it at each second. I just went ahead and did the total displacement at the end, or the average displacement. You can use this formula where you input V naught and then you change the T final so that way you're calculating your displacement at each second. In this case here, we can see that when we have a constant motion that is not 0 meters per second, our displacement graph will produce a diagonal straight line. Now let's get into some acceleration. In this case here, we can see that our velocity starts at 0 and it increases to 5 meters per second in 5 seconds. So in this case here, my first thing is to calculate acceleration, where I'm going to subtract the two velocities and divide by my 2 times, and that's going to produce an acceleration of positive 1 meters per second squared. Now, I can see that this right here makes that diagonal line. So there's going to be a triangle shape located underneath my velocity time graph. And in this case here, that means I'm going to use my accelerating displacement equation, which is the one for a triangle. So 1/2 base, which is going to be v final minus v naught times the difference in my time. So here we're going to get 1/2 times v final, which is 5 meters per second, times T final, which is 5 seconds. And my total displacement is going to be 12.5 meters. Again, you may use this equation. You may just vary the time and V final in this case, and that will give you your displacement at each second. Our last example is the most complex because in this case here, what I've done is I made sure that we have an accelerating motion in the negative direction, but also our initial velocity is not 0. So in this case here, we can go ahead and calculate our acceleration. We can see that V final is negative 12 meters per second, and we're going to subtract a negative 2 meters per second. So that'll produce a positive 2. Negative 12 plus positive 2 creates negative 10 divided by 5 is going to give us negative 2 meters per second, as we can see on the graph here. We can also calculate our displacement. In this case here, though, we're going to need to use that final example that we had. It's an accelerating object where the initial velocity is not zero. Therefore, we're going to have to do the sum of both the rectangle that's at the closest part to the x-axis, as well as the triangle that exists from negative 2 meters per second to negative 12. So you can see here we have that the rectangle has a height of negative 2 meters per second over 5 seconds. And then we also have 1/2 times that delta V of negative 10 times 5 seconds. If you add those all up together, we're going to get a total displacement of negative 35 meters. Again, you can use this formula. You can vary your delta T as well as your V final over time, and you can get each of those points along the displacement time graph. I do hope that you found this video helpful. Remember that your growth will be found in the journey rather than in the solution. So get out there and go try some practice physics problems. And as always, I'll see you in the next video.